along with this lesson, you're going to need the course pack page, which says Pascal's triangle to binomial theorem. What? Okay, what's binomial? Well, we know what a binomial is. It's something it's a polynomial that has two terms. What's a theorem? A theorem is a theory that has been proven. And Pascal's triangle we remember from before. So this is going to help us, Pascal's triangle is going to help us to expand binomials, and I'll show you what I mean. If we go down to example 1, it says, use the distributive properties to expand the following. How do we expand a plus b to the exponent 0? Okay, well this one's easy because anything to the exponent 0 is just, it's just 1. It's just 1. Okay, let's do the next one, a plus b to the exponent 1. That's just a plus b. Now, a plus b to the exponent 2 is a plus b times a plus b. So to expand this, it's a squared plus, we have an ab and an ba, so that's 2ab plus b squared. Okay, let's go cubed, a plus b cubed. Well, to expand this, it's a plus b times a plus b times a plus b, but a plus b squared is this, so I can just skip that step. And then I expand this. To expand this, we're going to have to multiply every term by in the first bracket by every term in the second bracket. We have 2 terms here. We have 3 terms here. We're going to end up with 6 terms when we expand. So let's go. A times a squared is a cubed plus 2a squared b plus ab squared plus a squared b plus 2ab squared plus b cubed. And let's collect the like terms. So we got 1 here and 1 here. We got 1 here and 1 here. And that gives us 8 cubed plus plus 3a squared b plus 3ab squared plus b cubed. Okay. Now, look at the example 2. It wants us to expand a plus b to the exponent 5. Okay, to do that, we would have to take a plus b squared, which has 3 terms, multiply it by a plus b cubed, which has 4 terms. We're going to end up with an expansion that has 12 terms, and I don't think we want to sit there and expand by multiplying. So we're going to use something called the binomial theorem, and it's based on Pascal's triangle, because if you look at what are the coefficients in each of these expansions, well, what's the coefficient in this one? Well, the coefficient is just 1. How about this one? The coefficient is the number in front of the term. So it's 1, 1. What are the coefficients here? 1, 2, 1. What are the coefficients here? 1, 3, 3, 1. Notice something? There you go. So the coefficients in the expansion are terms from the row in Pascal's triangle. Let's go to this box. Can you see a pattern? Is there a relationship between the exponent and the number of terms in the binomial expansion of a plus b to the n? There sure is. So, in the expansion of a plus b to the n, how many terms are there? Let's look. When n is 2, we have 3 terms. When n is 1, we have 2 terms. So, if n is n, then there are n plus 1 terms. Look at the coefficient of the first term and the last term, always 1 and 1, 1 and 1, 1 and 1. So in here, t1 is always going to equal to 1, and tn is always going to equal to 1. Okay, and what are the variables in the expansion? Well, when you're expanding a plus b to the n, the first term is always going to be a to the n, and the last term is always b to the n. Look here, a squared and b squared, a cubed and b cubed. So the first term in the expansion is not only this 1, but it's 1a to the n. And the last term is not only this 1, but it's 1b to the n. Okay, notice the sum of the degrees for each term. Let's look at what they mean by this. If we take, say, this one, this term has degree 2. Degree is the sum of the exponents, so of the term. So this one has degree 2. This one has degree 2 also because a is to the exponent 1 and b is to the exponent 1, and the degree is the sum of the exponents. And this one also has degree 2. How about here? This one's got degree 3. This is a squared times b to the 1, so the degree of this term is 2 plus 1, which is 3. This one's also degree 3. This one's also degree 3. So the sum of the degrees for each term is n. Coefficients of the expansion of a plus b to the n are the entries of row n in the Pascal's triangle. Pretty cool. So now when we do our example 2, we don't have to multiply them out. We can use the binomial expansion theorem. So a plus b to the n is, in our case, a plus b to the 5. What we do is we do this. We write out the terms of row 5 of Pascal's triangle. So row 5 is 1, 5, 10, 10, 5, 1. There's going to be 6 terms. So watch what I do. I'm going to go 1, and I'm going to leave giant spaces. 1, 5, 10, 10, 5, 1. Okay, now I wrote it all big and spread out for a reason, because now I'm going to fill in the variable part. What happens is the first term is to the exponent 5, and then it decreases by 1. The degree of the first variable is decreased by 1 each term. So a to the 5th, a to the 4th, a cubed, a squared, a to the 1, so I'm not going to write the 1. And then over here is a to the 0. But a to the 0 is just 1, so we don't see any a's. Okay. The b's will end up with b to the 5. And so the way to end up with b to the 5 is the first term has no b's, that's b to the 0. The second one is b to the 1, b to the 2, b to the 3, b to the 4, and there's our b to the 5. All of these terms are added together. And so in one step, I've done this expansion without multiplying anything. Cool? Yeah, very cool. Notice, how do you know that you didn't make a mistake? Notice this, the sum of the exponents, so the degree of each term should always be equal to n. Degree 5, 4 plus 1, 3 plus 2, 2 plus 3, 1 plus 4, and 5. And there you have it. So that's the binomial theorem. Let's turn to the back and practice a little. So we're on the next page. I'm going to do example 4 first. I'll do one of example 4. Then, no, you know what? Let's do example 4. I'll do the first one. You do the second one and check with me. And then we'll do example 5. Okay, example 3. Okay, first 4, then 3, of course. So now, it says, use the binomial theorem to expand and simplify. 2x minus 1, all cubed. Okay? So to make life easier, let's use a's and b's, because we can do a change of variables. So let a equals 2x, and b equal to negative 1. So what we really have is a plus b cubed. And that's much easier because we can expand a plus b cubed in one line and then replace our a's and b's. So a plus b cubed, well, you have to look at row 3 of Pascal's triangle for the coefficients, and they are 1, 3, 3, 1. Look how I wrote them far apart. The a's will start with a cubed, a squared, a, and no a's. The b's will start with no b's, b, b squared, b cubed, and then plus signs in between. Okay, now, for example 4. So what I was saying when it cut off is that it's not a hard question. It's just that there's a lot of simplifying, and you gotta make sure that you don't miss any terms or any minus signs. So after you've done simplifying everything, this is the final answer. Notice how when a term is squared, the coefficient inside the term is also squared. So look out for that. And here's a term that's going to be negative once you multiply everything out. So look for that. The next question is this one over here. And I'm going to ask you to do that one. So I'm just going to do the substitution part, and then you can pause the video. So again, we're going to write this as a change of variable, that a equals 3x and b equals negative 2y. And now we're just going to have to expand a plus b to the fourth. Now I've already written this, but the video didn't work, so I'm not going to rewrite it. I'll just show you my solution. It's going to start with 1, 4, 6, 4, 1, which are the row 4 of Pascal's triangle, and then you just put in your variables, a to the fourth, a cubed, a squared, a, and no a's, no b's, b, b squared, b cubed, and b to the fourth. Add your plus signs. Okay, and now we can fill in the 3x and the negative 2y. Okay, so pause the video here because I will now show my solution. Okay, here's my completed solution, and hopefully you got the same thing. So once again, it's an awful lot of writing, and you just have to be careful to, let's take for example this piece right here. The coefficient is squared, giving you a 9. This negative 2 is squared, giving you a 4. When you multiply, it's going to be that 6 on the outside times 9 times 4. And then you're also going to multiply the variables. So don't be scared about leaving multiple lines, doing this over multiple lines. You want to make sure that you don't miss anything. Okay, so that is example 4. Now let's just go up to example 3. I love this question, example 3, because it looks so bad, and really it's quite good. Let's go up to example 3. It looks like this. Okay, and example 3 says, okay, go backwards. So instead of expanding a plus b to the n, here's an expression. Let's write that as a plus b to the n. So really, it's factoring. We're writing this as something times something, which is a binomial to some exponent. So how do we do this? It looks awful, but really, let's count how many terms. 1, 2, 3, 4, 5, 6 terms. Well, if there are going to be 6 terms in the expansion, then what's n? Well, we said that in the expansion of a plus b to the n, there will be n plus 1 terms. So that means that n must be equal to 5. And we know the expansion of a plus b to the 5. That is a to the 5 plus a bunch of stuff plus b to the 5. And these terms in the middle we know will have coefficients according to Pascal's triangle. But it really doesn't even matter, because they're telling us that this can be written as a plus b to the 5. We'll believe them about the middle terms, and we just have to check the last terms, the first and last. So the first term is a 1. The last term is 32x to the 10. Well, the first term is going to be a to the 5. The last term is b to the 5. So we have two relationships. We have a to the 5 must equal 1, which means a equals 1. We also have b to the 5 must equal to 32x to the 10. Taking the fifth root of the coefficient and of the variable, so here I am taking the fifth root, it gives us that b is 2x squared. So this can be written as 1 plus 2x squared to the exponent 5. And if you want, you can take this just for practice and expand it out using the coefficients from the triangle, and you should get the same as the question. Okay, so really awful looking thing that's quite cute and not awful at all. Okay, and that is the last example for binomial expansion, so please review these notes as usual, and go back to class and we'll do the practice questions, okay? At this point, I just want to thank everybody for putting up with my terrible videoing skills, but it has been a learning experience. And I want to thank you for being patient and being receptive to the whole flipped classroom experiment. You've been really good about it, and I really appreciate it. And hopefully you found it beneficial. Okay, so we'll see you in class. Thank you for watching. Bye.